which will be given by Schmidt, and it's a bound on the quantum value of all compiled non-local games.
Okay, yeah, so thanks for the introduction. As you already heard, so I'll talk about a bound on the quantum value of all compiled non-local games. And this is joint work with Alexander Kulpe, Giulio Malavolta, Paddock, and Michael Walter. Okay, so let's start with some motivation. So let's say someone comes up to you and says, oh, this is a quantum computer. So you get some box, and yeah, there's the claim, this is a quantum computer. And then you can either say, oh, wow, great, a quantum computer. Or you say, well, does it have any quantum capabilities? Well, I don't know, right? But maybe I can interact with it and then say, oh, yeah, there are some quantum capabilities. That's great. And one approach to do this is so I call it the non-locality approach. So you either play some non-local game with some quantum advantage over all classical strategies, or you violate a Bell inequality. And with this, you can actually show that you have some quantum computer or at least some quantum capabilities. And yeah, furthermore, in this approach, so you can actually use it to actually verify quantum computations, as in the works of Reichert, Unger, Varisani, or the work of Giulio. And non-local games are really just information theoretics, so there are no computational assumptions here. Okay, that sounds great, right? But maybe there are some disadvantages. So what could be disadvantages? So for example, in the non-local game, you have two players. So in principle, you need two boxes, right? So two boxes is already not so nice. But you also have to ensure that the players are not communicating. So somehow you need two boxes, but one of them is here and one of them is very far away, which doesn't really work if you just have your one box and you want to see if it's a quantum computer or not. So one might ask now, okay, can I get the same? So can I prove quantumness just by interacting with a single device? And amazingly, this is actually possible. So yeah, we can, under computational assumptions by a result of Moadev, one can actually verify quantum computation just by interacting with one device. Okay, but now we have all this quantum, the non-local games literature. So is there some systematic link between the two worlds? And okay, so now we will review non-local games for a bit, and then we go to the compiled setting, and then we'll actually see how to get this soundness result, so some upper bound on the quantum value. Okay, so what is a non-local game? So in a non-local game, we have two players, Alice and Bob, and some referee. The referee sends questions from some finite input sets to the players, and the players answer also from some finite input sets. And there's some verification function that specifies the game, which is either 0 or 1. If it's 0, then the players lose. If it's 1, then the players win. And importantly, if the players receive their two questions, they cannot communicate anymore. And what's their goal? So the goal is usually to maximize the winning probability. So I call this here omega, and pi of xy is the probability of the referee sending x and y to Alice and Bob. And this v is the verification function. And then Alice and Bob they cannot communicate during the game, but they can agree on some strategy beforehand. And such a strategy usually yields this probability distribution, this PABXY, which is just the probability of Alice and Bob answering A and B if they get X and Y in the game. Okay, but now there are several different classes of strategies, and one can look at those, and one can try to find the optimal winning probabilities for those classes of strategies. So, for example, then the optimal value one can achieve, we call just the value. And there are several different ones. For example, the classical value is just, okay, let's say Alice and Bob, they just agree on some functions beforehand. So if Alice receives x, she answers with f of x, and Bob, if he receives y, he answers with g of y. And similarly, okay, so this is the classical case, but interestingly, now we can also use quantum strategies. So Alice and Bob, they share some entangled state, at least in the quantum setting, in some tensor product Hilbert space. Then they can use local measurements. And as seen, so one of the famous results by Bell, there are games, so for example, the CHSH game, where you can now do better with quantum strategies than classical strategies. But there are even more different classes of strategies one can look at. For example, the commuting operator value, which now, okay, the players still share a state, but it's just in one Hilbert space. But now the measurements they are allowed to do, they commute, which is why it's called this commuting operator value. And then the famous MIP star equal RE result, it also showed that, okay, also the quantum value and the quantum commuting value, they actually are different. And then, a bit away from the physical strategies, there are also the non-signaling strategies, which just say, I look at the correlations that could be possible for quantum strategies. So correlations, just the probability distributions for Alice and Bob. But there has to be a quantum strategy behind this. And what is nice about non-local games is if you play optimally, for some games, there's just a unique strategy that can do so. So what does this mean? So you can think about it as if, okay, so I'm the referee, I play this game with those two players, and now they perform optimally. Well, then, in a sense, they can only use this unique strategy. And this is used for example, for some applications such as self-testing and verification of quantum computation. Okay, so those were non-local games. So what could be? So how do we get from this two-player setting to just a one-player setting, but maybe with computational assumptions? So let's say we have some naive attempts. We just have one player. What can we do? Well, maybe we just send x and y at the same time, and the prover answers with a and b, but, well, then he knows everything, so there's not much to do, right? Then the second idea could be, well, let's first send him x, he answers a, and then, send him y, and he answers b, but still he has, knowledge of everything. So, but still the structure here already looks quite nice. So what can we do? Maybe somehow we want to make sure that, in the first round or after the first round, so when the player received x and answered a, he shouldn't really know what he got and what he answered. So what's the idea? We use some cryptography here. So now instead of just sending the plain x, we send some encryption of x, and we want that the prover, instead of returning a, he returns an encryption of a, which we call alpha here. And then the second round is exactly the same. It's just you get some y and answer b, but since you got an encryption of x and you answered with an encryption of a, you don't really know what you got and you don't really know what you answered, which is very similar to you cannot communicate with each other to tell you if you got x or answered with a. And then in the verification function, instead of this a, we look at the decrypted alpha and check if this is 1 or not. And this is the approach of Carlyle, Lombardi, Cantranwan, and Yang. And as I said, you encrypt Alice's part, and you leave Bob's part as is. But somehow you could now say, well, let's say I have a quantum strategy, then I somehow, if I get x, then I use my quantum circuit or my quantum measurements that I thought about before. When I get x, I choose this set of measurements, but now I just get some encryption, so I really don't know what I got. So we need some way to fix this, and this is using a quantum homomorphic encryption scheme, which allows me to compute unencrypted data. So somehow I don't really know what the encryption of X is, but with using this quantum homomorphic encryption scheme, I can basically compute on the encrypted data and get an outcome as if I would have known what I got and then encrypted it. Okay. So this somehow allows us to still use quantum strategies in this compiled game setting. So that's nice. But maybe you remember from before, in a non-local game setting, it's really information theoretic. So there's nothing about computational assumptions. But here we use this quantum homomorphic encryption scheme. So we also have to make sure that the player is computationally bounded, because otherwise he could just break it. So the strategies the player can use are just QPT algorithms. And the second thing I should mention is, so from this quantum homomorphic encryption scheme, this encryption of X, we shouldn't really, or the player should not be able to know what he got. So the post-measurement state after the first round, so when the player encrypted X and answered something, this should be computationally indistinguishable for any X1 and X2. Because otherwise, if it wasn't, then the player can get knowledge about the questions he got, which should not happen in such a scenario. Okay, so that's nice. So what do we know from before? So already in this first paper by KLVY, we know that so if we take a classical strategy for the compiled game, then the value or the winning probability of this is actually upper bounded by the classical value of the non-local game plus some negligible function. So this says, okay, I cannot, in a compiled game, if I just use classical strategies, I cannot do better than in the non-local game. And then, so as I said before, from this QHE scheme, one can actually use this QHE scheme to compile the quantum strategies. And with this, one can show that, for every quantum strategy with some winning probability for the non-local game, we can find some quantum strategy for the compiled game that does like pretty much the same, or just up to negligible. Okay, so what does this tell us? Well, still, if I have a non-local game with quantum advantage, then also in this compiled game, I know that in the classical case, I cannot do better than the classical value, but now I can do all quantum strategies, so I will always get this gap. But what I don't know is if I can even do better than quantum strategies, right? Because for now we just said, okay, I have the quantum strategies and I can compile them, but I don't really know if there's some crazy other stuff one can do. So so it's a good question to ask. How about quantum soundness? Can we get some upper bound on the winning probability of the quantum strategies of the compiled game? And what's the motivation here? So with those upper bounds, one can usually also infer some self-testing results, which allow for classical verification of quantum computation, for example. And this was only known in special cases. So for example, the CHSH game, and also one could get to XOR games. But before our work, we didn't know more. Okay, so we'll get this soundness result, and we'll actually prove that the quantum value of the compiled non-local game is actually upper bounded by the quantum commuting value of the compiled non-local game. And how we do this is 2 steps. And the first step is, okay, we forget about the crypto again in our compiled non-local game. But now we restrict the strategies of the 2 players to be very similar to the ones we get from this crypto scheme, but now in an idealized scenario. So as I said, in the compiled game, the post-measurement states after the first round, they will be computationally indistinguishable. And now, in this case, we really want to say, okay, what happens if they're exactly indistinguishable? So they're just the same state. And yeah, we call a strategy where this happens, we call it strong non-signaling. And as I said, this is really an idealization of the compiled scenario. And one could ask, okay, what are the correlations one gets? So what are the probability distributions for Alice and Bob? And the first result in our work is that if you have such a strongly non-signaling strategy, then actually the correlation, so the probability distribution, is a commuting operator correlation. So what does this mean? This means that I can write this probability distribution also as some measurements on one Hilbert space that commute. Okay, so that's really nice because this gives a sequential characterization of quantum commuting correlations. And I should say that for just quantum correlations in a bit of a different setting, there were also some results in quantum foundations. Okay, and now we get to the main result. So what is the main result? As I already said, so if we take a strategy for the compiled non-local game, then in the limit of the security parameter, we will never exceed the quantum commuting value of the game. So I wrote it here as this limit superior. And if you go with so lambda is the security parameter, and it goes to infinity, then we will always be smaller than the quantum commuting value. Okay, so how do we prove this? So in the first step, we really show that this computationally indistinguishability of the post-measurement states, they actually yield such strongly non-signaling strategies in the limit of the security parameter. And then we knew that for such strategies, the correlations we get will be commuting operator correlations. And this already means that the value has to be upper bounded by omega QC, so by this quantum commuting operator value. And what is still hard here is that, so in principle, so we have the security parameter, and for every different lambda, we can get different states and different observables or Hilbert spaces. So in principle, they could get larger and larger all the time. So what does it even mean to have some limit or something, right? And how we resolve this is we actually use operator algebras. So instead of just looking at the strategies with potentially growing Hilbert spaces and things where we cannot really do anything, we look at some universal algebra for, where we put all the strategies in, and then we can actually take a limit there, and that's how we get to this strongly non-signaling strategy. Okay, and then from our result, we can also get some self-testing result that is similar to the ones in the works mentioned before. Okay, then a short summary. So what did we get? So we obtained the first quantum soundness result for all compiled non-local games. What were the ingredients? So we had this alternative characterization of quantum commuting operator correlations, and then we used this universal algebra to make sure we can take the limit to get our result. And then from this, we obtained some self-testing. Okay, so what are some future directions? So we have this, we just have this limit superior, but we don't really know any quantitative bound. So for now, we just know that it goes to 0, but if it's a negligible function, that's not clear yet. Another thing is, so I said that we can compile this quantum, so the quantum tensor strategies. So we know that we can achieve omega q in the compiled game, and our upper bound is now omega qc. So it's not clear if we can actually get a soundness result for omega q, or if we can somehow compile also omega qc strategies. So this would be the correct upper bound. Okay, and as a last thing, so we use this QHE scheme to work in this compiled game setting, which has some cryptographic assumptions, and then it's always good to check if one can do the same thing, just with weaker assumptions. And there will be a post about this on Thursday. And yeah, with this, I thank you for your attention.
Question here, the microphone, please.
Well, I like your results. Have you even considered the non-signaling part? Because non-signaling games can be viewed as simultaneously communication from Alice to Bob and from Bob to Alice, right? I mean, you have the same strategy, but two protocols. Mm-hmm. And so in this, you could do, it's very canonical, you can do, compiling in Alice Bob and swap it around, and things could be very similar. Is that something you considered?
Maybe I don't. So what do you mean exactly? If you do like sequential
games have one strategy, some global strategy, which has an Alice to Bob communication protocol and a Bob to Alice communication protocol. That's well known, but not well known. I mean, experts know it, but nobody. Yeah. Anyway, that's a well known fact. So in principle, you could just use a one-way communication protocol in both directions, and your compiled version literally works in a way, right? You can do everything conditional on what happened before. It might be very interesting, because
I think
you have
it
only one
plausible.
value, though. You don't have two values to work.
Right.
Hello, thanks for the talk, it was great. So on your last slide, you mentioned that indeed, like previous bounds on the value of compiled games are slightly different qualitatively from what you've done, in that all previous bounds were quantitative, like they got a bound on the convergence rate, so they could be used in cryptographic applications. Whereas this one it's a different technique, so it cannot be, right? Mm-hmm. I guess two questions. Have you guys thought about a roadmap for possibly extending your results to cryptographically useful settings? And secondly, do you have any ideas about what compiled games could mean outside of crypto? I mean, mostly so far, the applications have all been crypto, right? But maybe you've thought about how it could be independent from crypto?
Yeah, okay, so for the first question, one can think about, for example, or think about NPA hierarchy. So I guess the problem about the negligible function is somehow that there are some weird non-local games, right? And then maybe you do some restriction. For example, you say, okay, in the NPA hierarchy, at some finite level, you achieve the value, and then maybe you can do some fun stuff to actually get there. So this was question one, and I think I forgot question two.
Question two was, have you thought about whether compiled games could have any meaning or application outside of crypto? Yeah.
That's a good question. I have to think about it.
Okay, thanks.
Any more questions? Okay, one last question.
Hi, thanks for the talk. Really nice results. Sorry, I just need to clarify a small point. So you prove by looking at the strongly non-signaling strategies, right? But this extends to all possible quantum strategies, like the bound of omega QC?
Say it again.
Your proof uses the, you look at the strongly non-signaling strategies, and then you use that you say that all of these give you scores that are bounded by omega QC, but then this holds for all quantum, all QPT strategies. Mm-hmm. So it's part of the result that you can pass from that setting to QPT strategies in general.
So you take any QPT strategy and then you get this bound. What is your question?
Just confirming that you can pass from the strongly non-local strategies to all QPT strategies.
Indeed, yes. So the idea is that, you take this QPT strategy, you find a strong non-signaling strategy, and since you have this bound there, you can infer it on the QPT strategy.
I see. Yeah. Okay, thank you.
Let's thank the speaker again. And